Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light, where we've been studying Christian Huygens' Treatise on Light. Remember that Huygens stated at the outset of his Treatise on Light that the aim of natural philosophy is not merely to describe a thing, such as light, but to understand its origin and its cause. So the subsequent 4 chapters, he presented his wave theory of light and argued that it provides a rational wave mechanical explanation for all of the known laws of optics. So you might remember the law of reflection, the law of refraction, and so on. But here's the rub. Huygens' theory required an all-pervading ethereal medium comprised of tiny, invisible, and extremely hard spheres to support light waves of such extraordinary speed. While a modern reader may feel uncomfortable with Huygens' constant references to the so-called ether, he or she must keep in mind that all other wave phenomena rely essentially on the existence of some type of medium to support the transmission of waves. After all, what would water waves be if you take away the water? What would sound waves be if you take away the air? And what would the wave in a soccer stadium be if you take away the cheering fans? In the same way, a wave theory of light would be nonsensical without a medium to do the waving, or so it would seem. In the upcoming readings, we'll find that Huygens' famous contemporary Isaac Newton offers an alternative to Huygens' wave theory. But before proceeding to explore Newton's so-called corpuscular theory of light, let's remain with Huygens for one more chapter to take a brief look at his wave mechanical description of how light from distant objects such as stars or church steeples, bend when passing through the Earth's atmosphere. So we're in chapter 17, and we're on page about 204. And in this chapter, what Huygens does is he talks about the refraction of light when traveling through air. And he's going to mention at the outset a few very unique phenomena that one can understand using the kind of technique that he has talked about in the last few chapters. The first one that he talks about is how the moon and the sun and the stars sometimes appear higher above the horizon than they actually are. So let's write that down. So some observations. And actually, I don't know if I have the ordering of these the same as Huygens, but let me just enumerate them. So the stars, the moon, and the sun sometimes appear higher, and by higher I mean altitude, above the horizon than they truly are. A second thing that he talks about is how things like church steeples are visible when they should not be. We'll come back to this, and I'll explain this in a moment. And the third thing is if you look at a distant object through a telescope, the telescope will not always, at all times of the day, be pointing at the same thing. So objects viewed through a telescope appear at different locations at different times of the day. So these are 3 of the interesting things that he notes that he's going to try to use his theory of light in order to understand. So let's jump right away to the figure, which is on page 205. This is figure 17.1. And in this figure, what Huygens depicts is a church steeple at point A and a couple of buildings, one at H and one at E, and then an observer at point B. And what he's imagining here is that there is light that is illuminating the church building, let's say, perhaps it's sunlight, and as a result, the light is bouncing off of the steeple at point A, so point A is serving as a spherical source of waves that are emanating away from it. Now, if light was traveling at the same speed in all directions, then you would have concentric circles centered at point A. However, as he points out here, the atmosphere has different densities at different altitudes. That is, close to the Earth, you have a high density air, and as you go up farther away from the Earth, the density is reduced. And accompanying this change in density or reduction in density with altitude, you also have a change in the speed of light with altitude. That is, at higher altitudes, higher above the surface of the Earth, the light travels more quickly, the waves travel more quickly, and at lower altitudes, the waves travel more slowly. Now, what does this imply? Well, if the waves travel more slowly, since the speed of light is equal to the wavelength times the frequency, if the speed goes down, then the wavelength goes down. And conversely, if the speed is higher, then the wavelength is going to be longer. So notice that in this diagram, the waves that are propagating upward, the compressions of the ether, you might say, or the distance between the peaks of the wave are farther apart. There's a longer wavelength for the waves traveling upward than for the waves traveling downward. That's because they're moving at a higher speed in the upper atmosphere than in the lower atmosphere. Now, what's the upshot of this? What's the point? He says, well, when we think about a ray of light, how we construct a ray of light is by drawing a line that is everywhere perpendicular to the lines of constant phase. That is, if we think about a ray of light, or rather if we think about a wave of light, if for some reason we have waves that look like this, then we would have to draw a line. So these are the wave fronts in this diagram. We would have to, in order to construct the trajectory of this ray, you'd have to draw a line that intersects these perpendicularly at every crossing. So this would be the ray picture of the light, and these would be the wave fronts. So what's happening in this diagram on figure 17.1? Well, if you were to think about a ray of light going from A, you'd draw a line from A over to the observer at point B, but you'd have to construct it in such a way that the ray crosses the constant wave, the wave fronts perpendicularly at every crossing. So you can see that the trajectory of this ray must curve. In particular, if we did not have the building at H, that ray would not be blocked. It would go from A and would curve down to the observer at position B. Notice that if you draw a straight line from A to B, that straight line would be obstructed by the building at E. So if the light did not have a variable speed with altitude and it was going in a straight line, the steeple top would be obstructed. It would be obscured from view from the person at point B. But because the ray curves and it goes over the building at point E and down to the observer at B, the person will see the steeple. He'll see the light coming from the steeple, but to his perception, it will be up at point D because he will be extrapolating from his perspective where that steeple must be in order for the rays to be coming into his eyes in the trajectory that they're going. That's what he's talking about in this figure. Now, why is this relevant not only for church steeples, but also for the comment that stars, moon, and sun sometimes appear higher above the horizon than they truly are? Well, if you go on to the next page, there's a depiction of the Earth's atmosphere surrounding the Earth. So Earth is at location AB. The atmosphere, admittedly exaggerated in depth, is at CD. And then you have some kind of starlight or sunlight coming in from the right side of the diagram toward the left. Those vertical lines represent the wave fronts coming in. And of course, as they hit the atmosphere and they slow down, the wave fronts are bent, as we talked about in the last chapter. Since they're bent, the trajectory of that light ray changes direction. And so whereas the star from which the light was coming maybe is over in the direction of E, it appears to the person's perspective who's standing at A to have been coming from a higher altitude up at point F. I don't think this is a great drawing, so let me redo the drawing for you to maybe give you a better understanding of what's going on. So let's suppose here you have the Earth like this. Let's make it brown. Since you're standing on the land, we'll make it brown and blue. And let's make the atmosphere kind of a light blue around the Earth, like this. And let's suppose you are standing right here. This is you on the top of the Earth. And let's suppose that there is a star down here at that location. And the starlight, notice that the starlight, if I were to draw a straight line, that star should be below your horizon. You should not be able to see that starlight. That black line represents your horizon. You can see everything up here, but you cannot see anything below your horizon. Well, what's the claim here is that if you think about a ray of light that would ordinarily be going in a direction so that you could not see it, when it hits the surface of the Earth, it bends, and as a result, you do see it. So it bends toward you. And from your perspective, it appears as if the star was located out here at some higher altitude. That is what he's talking about when he says that stars and moon and sun appear at higher altitudes above the horizon than they actually are. Now this might raise a question for you right away. How do we know where the stars, the moon, and the sun actually are? After all, we kind of discern where they are by looking at the light coming from them. So there seems to be an ambiguity here about how we would know where things actually are so that we could say that they don't appear where they actually are. Well, what one could do, I would imagine, is recognize that as the Earth rotates at a constant rate, these stars and the moon and the sun should be moving at a constant rate through the sky. Let's say 1 degree every minute. And if they move at a constant rate through the sky, then you should see them the entire time they're above the horizon go through the same number of degrees per second. But as they're close to the horizon and the light has to travel through more of the atmosphere, their speed is going to be different. You're going to detect a different speed. Furthermore, kind of going backwards in time, you might imagine you can calculate when that star should have been below your horizon by looking at how fast it's moving when it is over your head. And you can predict when that star rise should have been. But if the star actually is visible before that time, then you'll deduce that the star appears higher above the horizon than it actually is. This phenomenon, by the way, is called stellar aberration. It's something that Huygens and Kepler and other scientists at this time spend a good deal of time talking about. Another thing that he mentions is that objects that you see through a telescope will look like they're at different locations at different times of the day. Why might that be? Well, you might imagine aiming your telescope at a distant lighthouse that's out perhaps 20 miles out to sea. And if you put the crosshairs of the telescope and you focus them right on this lighthouse, let's say in the morning, if you go out and look at it later on in the day, the crosshairs may not be focused exactly on the top of the lighthouse. Why would that be? Well, throughout the day, the weather changes, the density of the air changes, and hence the trajectory of the light rays coming from that lighthouse are going to change. So as a result of that, the crosshairs of your telescope will not necessarily be focused at the same location throughout the day as the weather conditions change. Okay, there's one more figure that I'd like to point out here, figure 17.3. And this is a more detailed exposition of the kind of thing that Huygens has been talking about. He says, imagine that on the right-hand side of this diagram, you have a wavefront coming in from the right and heading leftward. That wavefront is denoted by the line AB. Furthermore, let's suppose that the speed of light is different at different altitudes. So up along the line AD, the light is traveling very quickly. But along the line BE, where the atmosphere perhaps is more dense, the light is going to travel more slowly. So if this line AB denotes the wavefront at a particular moment in time, then let's say a millisecond later, a moment later, how far will the light have traveled at the top of the atmosphere compared to at the bottom of the atmosphere? Well, in 1 millisecond, he says, the light emanating from point A will have gotten all the way over to point D, a fairly long distance because the speed of light is quite high. What about at the bottom of the atmosphere where the speed of light is low? Well, the light emanating from point B will only have arrived at point E. And similarly, as you go down from A down toward B, there are decreasing distances that the light, the spherical wavelets, will have traveled during that same time interval. That's what all these arcs are on the left side of the diagram. If you then construct a tangent to all of these arcs along the line KL, you will have the wavefront at this later time, 1 millisecond later, the point being that the wavefront will have bent. It will be traveling more downward. And likewise, you can do the same thing to arrive at the wavefront a moment later over at location MN. So again, this is a detailed exposition of how the wavefront will have changed its trajectory when traveling through an inhomogeneous medium where the speed of light differs at different locations. By the way, all of this stuff with Huygens is interesting because it has such broad application. He is using it to understand the propagation of light, but these ideas, Huygens principle, for example, are used not only for light. One can use them for sound, acoustics. One can use them for seismography, understanding the propagation of waves through the Earth's crust. One can use it for sonography and understanding how ultrasound imaging works in order to visualize babies inside of a mother's womb. So the kind of techniques that Huygens is presenting us with here are not only interesting, but extremely applicable in everyday technologies.